This is section 2.5, part D. We'll be looking at using inverses in applications or mathematical modeling problems. And there's one little thing about modeling problems that we usually change when we work with inverses. When we work with inverses and we're just working with generic functions that have x's and y's in them, we typically swap the x and the y in order to create the inverse function. The problem is that when we're working with applications, the letters often mean something. For example, T might stand for time, or P might stand for population. If I swap those variables, the meanings actually would get swapped as well, which is very confusing. So in order to avoid that confusion, we usually work with inverse functions without swapping the variables. Instead, we start, of course, by writing in the form dependent variable, whatever it is, equals our function. And then instead of swapping them, we just solve for the independent variable, the opposite variable. That preserves the meaning of the letters. We can still rewrite using inverse function notation, but we're going to be really, really careful with what those variables look like, and I'll highlight that as we work the next couple of problems. All right, we're going to start in the first example with what may be a very familiar formula to you. If you've taken some science classes, you've probably seen this formula for converting Celsius to Fahrenheit temperatures. I could write function notation here by saying that f is a function of c. So I'm going to say f equals g of c, 9/5 c plus 32. We're now going to look for the inverse function, g inverse. So I'm going to begin with my non-function notation equation. And to find the inverse, I'm going to skip the step about swapping the variables. Instead, I'm going to say, right now this is solved for f. Let's just solve for the other variable. Let's solve for c. And that's how we're going to create our inverse function. All right, because this equation has fractions in it, I'm going to choose to begin by clearing the fractions. I'm going to multiply both sides of the equation by 5. (5f). 5's cancel there, so I'd have 9c plus 32 times 5, or 160. Again, remember, my goal is to solve for c, get c by itself. So I'm going to subtract the 160, and I'll divide by the 9. So I could write c equals, I can leave it just like this, or I can write it as 5/9 f minus 160 over 9. That, if I want to give it inverse function notation, would be c equals, notice that the input variable is now f. So I would have to write that as g inverse of f equals 5/9 f minus 160 over 9. All right, if the original function takes a Celsius temperature and converts it into Fahrenheit, what does the inverse function do? Well, notice it does exactly the reverse, right? It takes a Fahrenheit temperature and converts it to Celsius. So the feeling of the inverse is still the same, even when we didn't technically reverse the variables. Okay. This inverse function converts Fahrenheit temperature 2 Celsius. And again, by comparison, that's exactly the reverse of what the original function did. So that inverse idea is still there. All right, the second part of this, it says find G of 45 and explain what it means. So G was the original. I'm just going to write out that statement of the original function in function notation. The input for the original function was a Celsius temperature. So I really am plugging in 45 in place of the C. And let's see here. I end up with 113. So again, I plugged in the C was 45. What I calculated was F, which was 113. So what this means is that 45 degrees Celsius is the same as 113 degrees Fahrenheit. All right, and in the last part of this problem, we're asked to find G inverse of 45. So let's see, it was right up here. I'm just going to once again steal this and rewrite my inverse function again. I'm still being asked to plug in 45, but notice this time the input is the F. This is 45 degrees Fahrenheit that I'm plugging in. So we put that 45 in place of the F. And we have 7.2 approximately. If I wanted to, I could change it to a fraction, 65/9. But if we were talking about temperature, actually probably the decimal form is going to be a quicker one to see about how warm or cold it is. So I'm going to call that about 7.2 degrees. So once again, our input this time was the Fahrenheit temperature. That's what became the 45. The output would be the C, the Celsius temperature. And so what this really says is that 45 degrees Fahrenheit is the same as 7.2 degrees Celsius. All right, let's take a look at one more example of an application problem, maybe one that's not quite such a familiar equation, or maybe not at all such a familiar one, since I guess we're going to start with data. We have a table of values that shows how percent of bodies cremated is actually increasing over the years. It's becoming a more popular option. And from 1980 to 2004, we've gone from less than 10% to almost 30%. I'd like to find a reasonable model for this data using the regression feature of the calculator. C is the percent of bodies cremated, and T is going to be years after 1980. So my T values here, 1980 is 0. That would be 5 years later, and then 10, 15, 20, and 24 years later. I'll go ahead and put this data into my calculator. In the Stat menu, I'm editing. Put my T values into list 1 and my C values into list 2. Right now, I don't necessarily know what kind of function is the best function to model that, so I probably want to go ahead and look at a graph to decide. Let me get my equation out of there and turn the plot on. My inputs, maybe from 0 to 25, and my outputs, maybe 0 to 30. And looking at those points, they look like a reasonably straight line, not exact, and I wouldn't expect them to be, but I can see that a straight line would come very close to all of those data points. So I'm going to go with linear regression here. Go back to Stat, and I'll calculate a linear regression model. And there's my slope and y-intercept. So it shows linear regression, and C equals f of t. We're going to go with 0.825. That'll be t plus 9.425. Notice that the regression, the correlation coefficients, R squared is almost 1, right? 0.995 is really, really close, so I'm very comfortable that this is a good model for my data. All right, next thing we're supposed to do is find the inverse for this function. So again, I'm going to go with the non-function notation, just the C equals. A little easier to work with algebraically as I go through. And although I'm not going to actually swap the variables, because I still want C to mean C and T to mean T, I am going to go ahead and solve for the opposite variable to get the inverse. So I'd like to solve for T. To get T by itself, I'll start by subtracting the 9.425. And then I'll have to divide by the 0.825. We can do these problems perhaps in a textbook where you're trying to compare your answer to the back, or in my math lab. Very often, rather than leave it in this form, they will divide it out like I was doing on the previous pages. And notice that the coefficient of C is really 1 right now. So, in order to figure out what the new coefficient of C, I would have to take 1 divided by the 0.825. And I'm going to go with 1.212. C minus dividing the 9.425 by 0.825, 11.424. All right. Now that that's solved for T, I can call that my inverse function. So I'm going to write that as T equals, the original function was f, so this will be f inverse of C. My input variable is now C. And there it is. So I've got the original function, input T, output C, and then I've got the inverse function, input C, output T. So ultimately, again, the roles of C and T have changed, even though I didn't actually swap the variables. All right, f of 20. Since this is f, I'll go back to the f function. This was a c equals, meaning I'm plugging in 20 for the t. 0.825 times 20 plus 9.425 gives me 22.9 approximately. I'm just going to notice that the c values in the table up here were all rounded to the nearest tenth, so I'm going to do the same in my answer. All right, what does it mean? Well, again, the value that we plugged in here was the t. And the value that we got out of this was the c. So this means 20 would be 20 years after 1980 in the year 2000. The percent of bodies that were cremated was 22.9%. We've talked about this in the past, but I just want to point out to you again that that's actually not the exact value that we found here. We found a slightly different value than what was in the table, and that's common. Our line's not going to go exactly through our points. It'll come close. All right, let's go on to the last question, finding f inverse of 20. Explain what that means. So our inverse equation, that's t equals, in this case it'll be f inverse of 20. I'll notice that c is 20. Looks like that when I plug it in. And let's see here, if I plug that into my calculator, I get 12.8 approximately. This is saying the 20 was what we plugged in, that was the C. The 12.8, what we got out of it was T. Since T is a number of years, I'm going to actually round that off, and I'm going to say that's about 13. So what this means is 13 years after 1980, or in other words, in about 1993, 20% of bodies were cremated. And again, this is another statement according to our model. It's always an approximation of reality. We're using mathematical models to predict. We know that they are not always going to be exactly the same as reality, but they should be good predictions if our model was a good model. All right, that brings us to the conclusion of section 2.5.